I'd like to thank the Microbiology Society for recognising virus snowflakes with this outreach award. This means a great deal to me. I grew up as a virologist, as a member of the society, and it was through going to its meetings that I developed the enthusiasm for general virology, which really informs this resource. So I'm very grateful to the society for recognising this. I'd also, of course, like to thank my nominators here at the MRC University of Glasgow Centre for Virus Research, or CVR, which is where I work. I was nominated by our director, Massimo Palmerini, and research manager, Maria McPhillips, with support for the application coming from Faye Watson, our engagement and communications coordinator. And the fact that collectively they put me forward to this, I think really demonstrates the way in which communication about our research is woven through the research culture here at the CVR. So thank you very much to all of them for that. So I'm very grateful, but to be honest, I'm also quite surprised to have been recognised for this year of all years, because 2020 has been a boom year for science communication for obvious reasons, and particularly for communication about virology. There's been a huge amount of really impressive and really important science communication done by researchers around the world whose, frankly, skills for producing high quality communication pieces and whose sheer force of personality for engaging with the public in challenging ways far exceed anything which I would be able to offer myself. And I don't want to detract from anything that any of them done. There's been some really wonderful things put forward, and this is only a small snapshot of them, although I had a lot of fun putting it together. But I'm actually really pleased that the Society has chosen instead to recognise a really, really low-key piece of science communication. Something we try to make clear to new students here in Glasgow is that if you have a particular set of creative skills, or if you're particularly good at engaging with people, different audiences, either in person or online, that's fantastic, and that should be celebrated and something you should really lean into. But if you don't necessarily find that comfortable, or it's not where you thrive, that shouldn't put you off science communication. All you need to communicate effectively about the research you do is a desire to share your enthusiasm for it. And Virus Snowflakes, the resource I'm going to tell you about today, really trades simply off that enthusiasm and a sheet of paper is all that's been involved in this. I'll explain what it involves, and it really is very simple. Here in Glasgow, as anywhere in the world where I think Christmas is celebrated in the winter months, there's a traditional decoration for paper snowflakes, and many of you will be familiar with this. In case you're not and fancy giving it a go, all you need is a piece of paper, and you just fold it to get a square, and then you fold that into a wedge, and then you snip bits out of the wedge to make a design which you can open up, and you get something resembling a snowflake, and they're very nice, and you can put them around the house. And I was doing this with my kids one year in the run up to Christmas, and I started to think, wow, these things, they look a bit like viruses. And this is, to be fair, the sort of thought you have when you work in a virology lab, but actually they do look a little bit like viruses. And if you tweak the design and get it ever so slightly altered, then the same thing goes. You take your paper, you fold it up into a wedge, snip bits out of the edges, and then when you unfold it, instead of a snowflake this time, you have, well, in this case, it's adenovirus. And that's it. That is basically the entire idea of resource I want to talk to you about today. It really was a very simple and straightforward idea. But I'm going to talk to you about it. So what I'm going to do is I'll start by answering the obvious question of why do viruses look like snowflakes? And then I'll talk a bit about how it was possible to develop this simple idea as a tool for science communication and for science education. I'd like to talk then about some of the ways in which people with some abilities to do things which I could not have managed myself took this idea and really ran with it and created some really exciting spin-offs from it. And then finally, I'll talk to you about ways in which this can be extended and hopefully encourage some of you to make similar designs of your own. But we'll start with this question of why do viruses look like snowflakes? And there is an affinity between viruses and crystals, which was noted very early on in the early days of virology at the end of the 19th century. And it was actually quite troubling to begin with. Both viruses and crystals at the time were existing in a rather uncomfortable space at the edge of the organic and inorganic worlds. Both of them seem to be able to grow without having all the normal properties of life. And of course, some viruses can actually be induced to form crystals themselves. So there's this troubling affinity between the two. And as people understood viruses more and more, it became clearer why this might be the case. So one of the definitive properties of viruses is that they take over a cell with their tiny genomes, and they force the cell to make infectious particles to transmit those tiny genomes from one cell to the next. And in a prescient and largely data-free paper, Crick and Watson pointed out that if you only have a small genome, then you only have a limited amount of space for encoding the proteins which can wrap up your genome in infectious particles. So it makes sense to have them in repeating arrays. A little while after that, Peter Wildey, after whom one of the Society's awards is now named, working in Glasgow with colleagues, got images of the structure of the capsids of herpes simplex virus, and was able to show that this formed regular icosahedra, which they demonstrated here in a rather lovely wooden model they had made. So viruses can produce these very regular structures through the use of repeating units. Now, they're not necessarily spherical, so one of the ways of doing this is to form a helix, as in, for example, tobacco mosaic virus, or perhaps more famously these days, Ebola viruses. And to be frank, these don't look very much like snowflakes at all. But many viruses arrange their capsids, proteins, the proteins which contain their genomes, into icosahedral boxes, essentially. And icosahedra, particularly when seen side on, do rather resemble the sort of symmetries you get in a snowflake. And whilst many viruses do this, other viruses will either, alongside that or as an alternative to it, steal membrane from the cell in which they're in. And the lowest energy state of membrane is to be pulled into a sphere in which all of the transmembrane proteins are more or less evenly distributed. So this too confers a regular symmetry, which is rather snowflake-like on a particle. And that can even pull some helical capsids into a more radially symmetric form. So not all viruses do look like snowflakes, but actually, because of the physical principles which form them, many of them do. And on that basis, I set about making some. And this was late 2019, and it was really just a fun thing to share with colleagues. So we had a bit of a quiz on Twitter to see if people could work out what the viruses might be from the little wedge designs, which targets a very niche intersection of people who are extremely interested in viruses and have decent spatial reasoning skills. And the idea became popular. It was really nice to see them turning up in Christmas photos from people's labs all around the world. This is a fun thing to do with colleagues, basically, more than anything else. And this, as I say, was Christmas 2019, a Christmas only slightly marred for most of us by some concerning reports coming out of a new viral pneumonia starting around Wuhan. And of course, things changed quite a lot, not that long after that. And so I returned to resource and thought it might be a good moment to expand it further. There might be a desire for people to know a bit more about viruses than they had before, and to put a bit more effort into making this suitable for the general public. And it turns out that this is actually quite a flexible format for communicating in. Simple and affordable. Obviously, all you need is a printer and a piece of paper. You can approach it in many ways. You can sit down and cut out a design like this individually. You can work it into a range of different group activities, from classrooms to science festivals. Importantly, it's based on active learning. So you can't just read it and move on. You do actually have to engage with the resource to create the snowflake. You have to think about the spatial arrangement of the components to produce the final thing. The fact that paper isn't square means there's a little strip down the edge where we can put in some key concepts about viruses and vaccines. And because you have to make active choices about what information to include, something I'll come back onto later in the talk, it's possible to embed information in this at multiple levels, from the very basic introductory concept of infectious disease being transmitted by particles, and this is how it works, through slightly more complex ideas about genomes being put inside particles, through to embedding the sort of information which we teach to virology when we're teaching undergraduates and postgraduates basic principles about virus structure and function. And all of those can be put in there at the same time. And so that was the basis for what we did. I expanded the resource to include a wide range of different virus particles, including some more challenging ones like HIV, where there's a bit of extra folding to show the maturation of a capsid, or viruses with more complex multi-layered capsid structures like the rotaviruses or blue tongue virus. Also, of course, because this was now being done in 2020, it was important to include SARS coronavirus 2. But it was also, in the run-up to Christmas 2020, possible to include designs which explained how the vaccines against SARS coronavirus 2 worked, and to show the virus neutralized by the antibodies they elicited, and to show how those were effective in preventing the virus from binding to new cells. So it's possible to embed some very topical information in these designs as well. In other words, we had some intended learning objectives. We could have a set of designs which presented viruses as being both natural and beautiful, rather than some unknowable, invisible, and rather alien force, but part of a natural world, and to be feared no more or less than any of the rest of it. It was possible to take a selection of viruses which didn't just take the standard line of these are human pathogens, but also to include some of the more engaging and less commonly discussed areas beyond that. So, for example, there's the giant Mimi virus and the smaller Sputnik virophage, which parasitizes it. There's the Zinella virus, which the majority of those of you listening to this will be infected with right now without experiencing any symptoms. And as I said, a range of different capsid types, as well as all of the 7 Baltimore groups of viral genome. It was a format in which we could talk about infection, about vaccination, and to cover a wide range of viral genome and capsid types, as I just said in there. And this had, to be fair, a fairly soft launch through Twitter, but it really took off. It was nice to see it turning up being used in schools, often around end-of-term tests, turning up in people's homes, in locations around the world. And then also to see people starting to take these designs and doing more with them. So because there's now a set of vector art graphics depicting viral capsids, people could do various different things with them. And these designs are incidentally available under a Creative Commons license. I'd be delighted if you made all sorts of different use of them, if you'd like to do so. Some people did some really interesting things. So Vittorio Sagiomo, who does a whole range of really interesting 3D printing stuff through his research, also 3D printed a load of snowflake designs for Christmas decorations based on this, and you can download those and print them yourself if you're interested to do so. There's a link. Boris Alanou and Marine Petit took a slightly different route. They used laser cutting of wood to make a series of very attractive designs. There, I think, once again for decorations, although they look rather like coasters in there, but a really nice finish they got on those. Kristen Henry produced a mindful video game to begin with, simply showing them falling down the soothing snowflakes. But then as the year wore on, I think she decided it was time to fight back and introduce a Space Invaders element where you could use a syringe to shoot vaccinations at all the viruses and pop them. And Liza Wolfson, a scientific artist who some of you might know from the coloring book she developed for Microsoft a few years ago, realized that if you stick these things on windows, then you can get some really interesting shadows, and started producing immersive viral art based on those. So there was a range of really unexpected responses to this resource. And something really nice that happened as well is that people started making their own snowflakes here. So here you can see in some Christmas decorations up at the Roslin Institute, this picture taken by Fiona Sargerson, some bacteriophage coming in and parasitizing some of the viral snowflakes they have there. And it was really nice to see people picking up this idea and developing their own versions of the snowflakes. And so in case you're interested in doing that for yourself, I thought what I might do is just take you through the process, which is involved in designing one of these things. And so I'm going to do that with the virus, which slightly inexcusably never made it into the 2020 release of the snowflakes. That's one of the viruses with the best studied of structures, poliovirus. You can see here, a very nice icosahedral, somewhat snowflakey design. So the first thing you need if you're going to make a virus snowflake is you need some sort of template. And somewhere I found myself turning again and again is a website which will be familiar to, I'm sure many of you have an interest in viral structure, which is Viral Zone, a really wonderful encyclopedia maintained by Philippe Lemessier at the Swiss Institute of Bioinformatics. And Viral Zone has these lovely clear schematic illustrations of really a comprehensive set of different viruses. And here's the one of the enteroviruses, which includes polio. But if you're interested in the subject, then you're likely to want to go a bit beyond that and to pack in as much information as possible. So the next step is to sit down and do some reading, which is really the most enjoyable part of this process. So what are the key features of polio? Well, the viral capsid has been studied in great detail there, so you can see the arrangement of the proteins is understood very, very well, as is the arrangement of the RNA underneath. It's a single-stranded RNA genome. We know that it's wrapped in layers underneath, but now we need to start making some choices here about how best to represent that, because that's not going to be terribly clear with a radial symmetry applied to it. It might be clearer that it's single-stranded RNA if we represent it in a slightly less realistic way, but we should still have it contacting the capsid in the way that it does in reality. You can also see some quite distinctive valleys and turret-like protrusions from the capsid, which is going to be important later on in defining the shape. Some of you may also be aware that polio has an interesting relationship with lipids. So there's a pocket inside the capsid where lipids sit. This can also be targeted by antiviral drugs, quite near the five-fold axis, and that's quite important to how the virus then coats. So it would be nice to stick that in there as well. Who will care about that? Well, really, probably only people who are studying virology at an undergraduate level and above, but it'd be nice to stick that in there for them as well, and frankly, for me. So let's see if we can get that in there as well. So we have our design. We put that into a vector art editor. If you have Adobe Illustrator, you could use that, but this is Inkscape, which is the open source alternative. You need some guidelines, so a circular one to define the overall shape of a snowflake, and then the lines of symmetry. So there are 6 of those here. And actually, I'm just going to jump in now straight away and overlay that nice slice through the crystal structure we had there before. We need to rotate it around so that it's lined up with a line of symmetry through one of the major features. You can see we've just done that there. Let's zoom in. So now in orange, it's not super clear there, but I've just started tracing around the outside of the capsid there. We can take away the guides now because we've got that in there, tracing around the underside of the capsid as well there. And now the genome. So we decided before we weren't going to show all the layers of that, but we'll just put in a bit of a wiggly line to show single-stranded RNA, and that needs to contact the capsid, ideally roughly the right point, although you need to now start thinking that you're going to be cutting this with scissors, so you need to be able to cut to all the points from the edge of your wedge. From one side or the other, so you can't have it contacting too many points. So we'll do that, and that gives us our basic design there. We've started to make some of those edges curly. We can then, we need to put in a pocket factor. So we've got our images of a pocket factor, some rather old, some newer. That gives us a rough idea of the scale. You can't make it too fiddly because we've got to remember people are cutting that out with scissors. So that's gone in there. And yeah, I think that looks about right. So there's our design. Nice symmetrical design there. Let's just rotate it and put it in. And, oh, okay, so that's not quite what we'd hoped for. And what's gone wrong there is a problem I didn't really say before, which is that icosahedra look hexagonal in projection, side on, but if you cut a slice through them, they're not hexagons. So that's a bit of a nuisance. So what we're going to have to do is we're going to have to cheat, and what we're going to do is we're going to impose symmetry which doesn't really exist on there. So we're going to try and get features which we would see side on all into the same plane. And the way to do that is just to take our current image and flip it, so we've got the same symmetry features on both sides. Okay, so we can now redraw that a bit to get the canyon and pocket factor on the other side as well, making sure we can still cut through for genome. There we go. And now if we expand it, good. Okay, so we've now got all of the factors there, which we want to see. We've got the single-stranded RNA genome, we've got the capsid, we've got the pocket factors, and it looks in a slightly cheaty way like an icosahedron, so that's good. So we can now take that, and we've got an outline here which is designed to take these designs. We can drop that in, get it the right size. We just want one wedge for people to cut out, so they have to think about it as they go. And then we've got some bits on here where they can, as well as the instructions about how to do it, where we can write about the virus, and also some bits about the virus particles. So what are the key things we want to know about the virus? We want to know how it spreads, a bit about the diseases it causes. Very important about vaccination, particularly about polio and some of the challenges to vaccination. Those are key public health messages. They should definitely go in. And then about the virus particle, single-stranded RNA genome, that it's icosahedral. We need to explain what the pocket factors are. So all that information can go in. And that's our finished sheet for poliovirus. And now we can have a look at it. So we have printed that out there, and cut the information sheet off. We can keep that for later, fold it up, snip away, and then unfold, and there we have a poliovirus snowflake. So that's the approach you can take, and all it really requires, other than the willingness to sit and think about shapes with a vector editor, is being sufficiently interested in the viruses to do that reading to begin with, and to really dig into what the key features of the viruses are. And of course, for me as a virologist, that is the most interesting part of the process, and trying to communicate that is the whole point of the resource. So hopefully some of you might want to do something similar as we come up towards the festive season this year. From my point of view, it would be great to do some more of these for Christmas 2021. In particular, I'm aware that although I have tried to do a first pass at covering key topics in virology, there are some really important things missing. We don't have any bacteriophage in there at the moment. We don't have any plant viruses. There are some major human virus families which are not yet represented. So if you do have a favorite virus which is missing, particularly a virus with a good story to tell about it, an unusual story, one you think people will be interested in, if you are slightly offended that I've missed out a very obvious virus, then please let me know. There's a survey running at the moment, and there should be a link along with this talk. Please do pop in there and tell me. Please don't tell me to make extended filamentous viruses like Ebola unless you have a good idea for how to do it. And if you do, of course, I'll be delighted. I'm going to really enjoy doing some more of these in time for Christmas 2021. I'm really pleased that this outreach prize has been an incentive to do that. But I can see that I'm going to find it harder than I did before. Not because there's any shortage of viruses with interesting stories to tell. I think that's a more or less infinite resource. But because I never really spoke about why I spent so much time doing this. For me, 2020 was really hard, and I think that's true for most of us. And there were times when it was really helpful to just sit quietly and lose myself in a craft activity like this, and to think about interesting biology, but not really have to think too much about how this particular virus had changed everything. So spending time doing this wasn't just a piece of outreach, it was something which was really helpful for me as well. I can see now that things are changing, and thankfully for me, it's going to be less important to spend that time by myself working on these designs. And although that might make it a little bit harder for me to finish off the resource in the way I fully intend to do, nonetheless, I think that too is something to be very grateful for. So I'd like to thank the Society again, and I hope that by the time these are useful again as Christmas decorations, the world will be a much less fraught place. Thank you all very much.